Alrighty, good morning everybody.
Good
Welcome
morning,
back
Lydia.
to Abstract Algebra. And a good morning to you too, Lydia, of course. Hope y'all are enjoying this great Thursday morning. Plan for today is we're going to stop the review and start jumping into some new stuff, with a little bit of review along the way sprinkled in. And today we're going to be talking about the characteristic of a ring. What that means, what can we do with it, what does that tell us about properties of the ring? That's going to come up a lot later in this course. Got office hours today. See, Lydia, I wrote record for my office hours so I wouldn't forget to record. And now I have Parker, you probably can't see, who's sitting over in the corner with my recorder.
He's the easiest of all of us to see.
Oh yeah, no, he is.
Yeah,
There's a couple of you. That's true. Anyways, got office hours this afternoon, 1 to 2. Tomorrow morning, 11 to 11:45. Monday, 11 to noon and 1 to 2. Why only until 11:45? Well, because this Friday will be the first official math lunch of the semester. Starting at noon to 1 this Friday. Make it if you can. If you can't, sucks to be you. Yes, OS. Don't forget to all have a homework set that's out. It is homework 1. It will be due Thursday, a week from today. After today's class, you should be prepared to tackle said homework. Oh, hi, Shades. Any questions or comments before we get started for today? Why did the teacher confiscate the rubber band in algebra class? Teacher had to confiscate the rubber band because it was being used as a weapon of math distraction. Mass destruction pun. Alright, so last couple classes we kind of did a review of many of the highlights of Math 410, particularly with regards to groups, rings, fields, kind of some of their basic properties. I'm going to pass the packet out in a second. Please be patient.
She grabbed one. I thought
No,
this was just a
I gave her one because she wanted to know something, but lost my train of thought. Talked about all of the basics. Today we're going to start talking about some new things. There will be some more reviews sprinkled in throughout. Like particularly, there's some stuff related to like maximal and prime ideals that those of you who had me for 410, we talked about it like the very end of last semester. That will come up again, but we'll kind of sprinkle in some review of that as time goes on. Today, we're going to talk about the characteristic of a field. Or in other words, how many times do you have to add 1 to itself in order to get 0? Where do you have one? So pass that back. 3 for you. And 1 for you, Lydia, but you're going to write yours out. Alrighty, so here's the scoop. We're going to assume that R is some ring, and we have to assume that it has a multiplicative identity, 1. And we're going to define the characteristic of R to be the smallest number of copies of 1 that you have to add together in order to get to 0, the additive identity element. So, R. 1. And then the characteristic of R. Which often will get labeled as like car R. Car R is the smallest natural number, so the smallest positive integer, such that if we add 1 to itself with n copies, we get the 0 element of the ring. And if no such n exists, meaning if you keep adding 1 to itself over and over and over, and you never get back to 0, we just say that the field has characteristic 0.
Just saying it has characteristic infinity doesn't make much sense.
I mean, we could, but then a lot of the later theorems and stuff would be more awkward to state. So, yeah. So if no such thing exists, you say characteristic of R is 0. Yes, Jonah.
Does the ring with only one element have characteristic?
Does the ring with only one element have characteristic 1?
The 0 is what I was thinking.
Characteristic 0. Well, suppose your ring has one element. We'll call it 0. Then 0 has to also be 1 because it's multiplicative identity. After all, 0 times 0 is 0. So in that case, how many copies of 1, in this case 0, do you need to add together to get 0? I would say you need 1 copy, and I would say it is characteristic 1. So let's look at some rings. Let's look at the integers. Z mod NZ, M2R, and just for funsies, continuous functions over the rings. I want to know what the characteristic of all of these is. So let's start with the integers. Jackson, how many times do you have to add 1 to itself in the integers before you get 0? Or is that not, or
I mean,
does
Does
that never happen so you have characteristic 0?
Yeah.
What do y'all think? Characteristic 0? Yep, I'm inclined to agree. Characteristic of the integers gonna be zilch. No matter how many times you add 1 to itself, you're never going to get back to 0 in the integer. So we say that it's a ring of characteristic 0. How about Z mod NZ? Matthew?
Is that probably gonna be n, I'm assuming?
Well, if we added like 1 to itself n times, which would eventually get you to n, which is going to be represented by 0 in Z mod NZ. Does that sound like characteristic n to you?
Yeah.
I agree. Turns out characteristic Z mod NZ, it's going to be n. And yes, Jonah, as a subcase of that, if you let n be equal to 1 so you get the trivial ring, then you would get that the trivial ring has characteristic 1. How about 2x2 real matrices? So that forms a ring under matrix addition and multiplication. What's our 1 element in this ring? So in other words, what element corresponds, Andrew, to the multiplicative identity?
1 0 0 1.
Yeah, so our 1 element in this case would correspond to not a number. Here 1 is just literally 1. Here 1 is technically represented by 1 bar, the coset in the integers of nz corresponding to 1. Here our multiplicative identity, our 1 element, is the 2x2 identity matrix. So Isabel, how many times do we have to add the identity matrix to itself in order to get back to the 0 matrix? 0, 0, 0, 0.
Oh, you can't do it.
You can't?
No.
What does that tell us about the ring?
Characteristic 0.
It's characteristic 0, indeed, yeah. No matter how many times you add this matrix to itself, you're never going to get to the 0 matrix. Or again, additive identity in here is a matrix of all zeros. So we're going to say this this ring has characteristic 0. How about C0R? And note the fact that there's 0 in there doesn't automatically mean it. The fact that there's a C followed by a 0 doesn't mean that the characteristic is necessarily 0. First of all, Isaac, you remind us, what is this ring?
That's the ring of continuous functions.
Yeah, it's the ring of continuous functions over the reals.
You know, it says CO.
Yeah, well, it's 0 times 0 here refers to 0 times differentiable, which we just take to mean continuous.
It also has characteristics 0.
It also has characteristic 0, huh? All right, what's your 1 element in this ring?
F of x equals 1.
So we have a 1 element that's defined by f of x equals 1. because if you multiply that function by any other function, you just get the other function. Eleanor, what's the 0 function in this ring? F of x, different letters, please. Equals 0. Because if you multiply that function by any other, or not multiply, if you add this function to any other function, you just get that other function. And how many times do you have to add the function f of x equals 1 to itself in order to get to the 0 function? 0 times? How do you add something 0 times?
You don't.
You forget about it. Well, the answer I'm looking for is you can't.
Yeah.
And so yes, it does turn out that this is a ring of characteristic 0.
But so would C1 and C2.
You could replace this 0 with literally any n, or infinity if you're feeling frisky, and it would still be a ring of characteristic 0 for the same reasons, in fact, because this is the multiplicative identity and this is the additive identity of no matter how many times you want to be able to differentiate your functions. These are constant functions. You can differentiate them until the cows come home. You're going to be getting a lot of zeros. So, yeah. Got a lot of rings of characteristic 0 so far. And wouldn't you know it, our one finite ring happens to be the one that has characteristic n. Coincidence?
I think not.
Actually, yes. Let's look at an infinite ring that has finite characteristic.
Oh.
You've been tricked so easily. Here's one that I chose specifically for you, Parker.
Oh.
No,
What's
no,
it?
Wait a minute.
Let's look.
Let's talk about this.
Let's talk about this. You don't have to do this. I'm on page 2 now.
Oh.
This is not racist. Let's look at the ring of polynomials over Z mod 3Z.
Not to him.
Why? Oh, that's so awful.
Oh no, the horrors. So what is this mess? Well, it's just like a regular, think about it like this. It's the integer polynomial ring, except except the scalars out in front of your powers of x are being treated as scalar values mod 3.
So could you make it like a proper quotient ring by saying ZX mod 3ZX?
Would that be isomorphic to this?
Would it be, yeah.
That would actually be a fun homework question. You could, yes, and that'd be a fun application of first isomorphism theorem. But yeah, you could do something like that.
So this is a quotient ring, whereas Q of X is not.
Well, technically this is not a quotient ring.
Oh.
Technically, this is a ring, a polynomial ring, where the coefficients are coming from a quotient ring, but that doesn't make the ring itself a quotient ring. There's a subtle distinction in that, like the powers of x, for instance, those are not like cosets.
Because our elements are.
Those are just the indeterminate x to various powers. Let's do a little bit of algebra here. I'm sorry, Parker. By which I mean I'm so glad to get to do this to you. You have no idea. Looking forward to this one.
It's not fair.
So, alright, let's do a little bit of foiling. Let's take 2 bar x to the 4th plus 1 bar x cubed, and we're going to multiply by 1 bar x squared plus 2 bar. That's right. We need to do some foiling and modular arithmetic at the same time.
Oh boy.
Oh yes. Hey Parker,
Oh yeah, what's up?
what's the first thing we do when we foil?
Well, I would say you want to multiply all the terms together, wouldn't you?
Yeah?
I mean,
So what do we get when we multiply the first 2 terms together?
what you get, well, it's modular, so it's still going to be 2 bar, but you're going to get x to the 6 as well.
Yeah, we're going to get 2 bar times 1 bar, x to the 6th. When we take these, when we combine these first terms together. Let's see, FOIL, F-O, outside. Andrew, how about the outside two terms?
1 bar x to the 4th.
Yeah, we're gonna get 2 bar times 2 bar x to the 4th, which in the next step, this will simplify to 2x to the 2 bar x to the 6th. Keeping in mind that 2 bar times 2 bar is what?
0 bar.
0 bar. What ring are you working over?
So,
It's 1 bar.
Oh,
2 times 2 is 4, which is congruent to 1 mod 3.
Eleanor.
I think I was doing 0 mod 4.
Oh,
So I asked, what ring are you working over?
Yeah, not this one.
All right, Eleanor, answer me this. First outside, inside. What's 1 bar x cubed times 1 bar x squared gonna give you?
That's 1 bar x to the 5th. Because I can do 1 times 1. In any way, not what I can do.
Very good. And finally, last two terms, the Lincoln. What's 1 bar x cubed times 2 bar gonna give us?
2 bar x cubed.
I didn't hear you because someone was saying something.
2 bar x cubed.
Yeah, we'll get 1 bar times 2 bar x cubed, which comes out to plus 2 bar x cubed. So basically, foiling works the same way that it does over regular integer polynomials. Kind of the only difference here is you have to multiply the scalars together, and when you do this multiplication, the multiplication is actually taking place in z mod 3z, so you have to do multiplication mod 3 to simplify your scalars down. Eleanor, you look like you're about to explode. Do you have something to share?
No, I just can't count it.
Oh, you're just
More-
embarrassed, okay.
No, it just becomes more and more obvious every day because there have been so many things already this semester.
All right.
I wish it has been proved that I cannot.
All right, well, let me ask you this. How about the 6 and the 4 and the 5 and the 3? Do we need to mod those out by 3?
No,
Why not?
because it's X.
It's, they're polynomials, so those are not in the same, they don't come from the same ring.
Correct. Yeah, the x, yeah, and here's kind of the distinction that makes this technically not a quotient ring, it's just the scalars happen to be coming from a quotient ring, is that the powers of x are not kind of following the same z mod 3z pattern. The z mod 3 just tells us how do the scalars interact with each other. But,
We already had an X to the 4th when we started those, and an X cubed, which would have had to be modded out.
this is true. Well, this is true. Well, I mean, didn't have to, but if we wanted to simplify our answer fully, we probably should. Yeah, Jonah?
But is X taking values from Z mod 3?
X isn't taking anything.
Oh,
X is just an indeterminate.
I mean, but are those?
Do you want to be able to plug in values for X, you mean?
Right.
It depends on the context, but not necessarily.
Okay.
I would say,
Because if you could only do that, then you might be able to simplify it. But yeah.
Technically, values of X that we could plug in don't have to be in Z mod 3Z. In fact, we're going to be doing a lot of plugging in values in this sort of ring from a lot of other rings later in the semester. For instance, we might be plugging in I for X. That'll be a kind of go-to example, or square root of 2 we might be plugging in for X. So the values you plug in for X, first of all, you don't have to plug in things for X necessarily. Oh, I miss your evil laugh. The values you plug in for X, first of all, you don't actually have to plug in anything for X necessarily in order to talk about the ring. And second, even if you do, what you plug in for X could be anything. It could be I, it could be square root of 2, it could be something in Z mod 3Z, it could be Eleanor, it could be whatever you want to actually plug in for X. Yeah, 1 bar times Eleanor to the 4th. You know that. Oh, excuse me, 0 bar times Eleanor to the 4th. In her ring.
That just makes me look
Oh, I
better.
didn't know.
So, here's a question. What's a characteristic of this ring?
Eldor, can you do
Lincoln? 3. 3? So, what's the one element, the multiplicative identity here?
1
Bar.
bar. That's true, it is 1
Well,
bar.
I mean, y'all laugh at this, but technically this is important.
It's true,
Is it like the integer one, or is it actually 1 bar?
it's 1 bar.
It's 1.
It's 1 bar because it has to come from the scalar value corresponding to 1, and the scalar value corresponding to 1 in our scalar ring here would be 1 bar. So our 1 is equal to 1 bar, and so since you have to add 1 bar to you have to have 3 copies of that to get to the 0 element, which would be 0 bar. This would be 3. Hey, Pete, how many elements are in this ring?
Balance.
Infinite, even though the scalars, there's only 3 scalars to work from? Indeed. Because while you only have 3 values to choose for each scalar, you could have infinitely, you could have an arbitrary number of powers of x showing up in any term here. So this is actually an example of an infinite ring that still has characteristic non-zero.
I still don't think it's a collective.
Well, all right, let me put it to you this way. The integers have characteristic 0, therefore a ring constructed using the integers is probably, or the reals for that matter, which also have characteristic 0, as a ring. And a ring constructed using those as kind of its base pieces is probably going to have characteristic 0 as well. Whereas here, this one's being constructed with Z mod 3 as sort of the scalars, the base pieces. So the characteristic of this ring is going to somehow rely a lot on the characteristic of Z mod 3Z, which happens to be 3. Any other questions or comments about this ring? Yes, we are going to be... No, I didn't just introduce this ring to Agonize Parker. That was only a perk. Because we are going to be working with these sorts of rings a lot throughout the semester. Not necessarily Z mod 3x, but like different types, but polynomial rings quite a bit, where the ring of scalars that we have to work from doesn't necessarily just have to be something you're familiar with, like the integers or the reals. Speaking of which, let's do another one that's a little bit zany. Bless you. Let's look at the ring of 2x2 matrices, where matrix entries are coming from Z mod 4Z.
Now I can.
Yes, now you get to do it. Aren't you happy?
You're gonna confuse it and say 3.
But here's the thing, Parker, 1 plus 2 is 3 in this matrix, in this ring. So it would be
And
fine.
2 times 2 is 0.
That's true.
All right, Eleanor, let's see if you remember your linear algebra.
Okay, so you have
What's the top left entry here?
6 bar, which is equivalent to 2 bar.
How'd you get 6 bar?
Because it's 1 bar times 0 bar plus 2 bar times 3 bar.
Yep, so we get 1 bar times 0 bar plus 2 bar times 3 bar. And that's just normal matrix multiplication. Dot product of first row with the first matrix with the first column of the second matrix. And I don't want to write this out for all of them, but if you simplify this, now you have to actually do your modular arithmetic. This will come out to 6 bar,
Which is 2.
which is the same as 2 bar.
And then you have 1 bar.
And-
then
Up here?
Yeah.
Do we-
1 bar times 1 bar.
1 bar plus 4 bar is 5 bar, which is 1 bar.
Yeah.
Yep. So this comes out to 5 bar, which is in fact 1 bar.
Yeah, and then you get 9 bar, which is 1 bar.
Yeah.
And then 2 bar plus 6 bar, which is 8 bar, which is 0 bar. Yes.
It's still the evidence we have, you only count as A4.
Yes. I think this is what I'm discovering.
That's what it would be if modular arithmetic were to work in the usual way.
What?
When in fact, it does work in the usual way, so that's
Thank you. I knew that.
Yeah, just like your moral of the story though is just like your ring of scalars in a polynomial ring doesn't necessarily have to be a nice friendly ring that you're working with. Same is true for matrix rings. You could have your individual components in a matrix ring. You could have it be reals, which is what I assume you're most used to, or integers, or polynomials or Eleanor or whatever you want, as long as you have a way of adding and multiplying elements using dot products. And in this case, the matrix multiplication works the way it normally does, but the way you then actually have to compute the dot products relies on addition and multiplication here, mod 4, instead of the usual stuff. If you really want to look at a spicy ring,
Oh boy,
Because
that's
tensor
what.
bars.
Wait, no, but you could do Z mod 3 instead of R there if you wanted.
You could do another.
You could do
matrix.
Yeah.
You could do it.
but you could have you could have matrices where the individual elements are matrices if you really wanted to.
in which the individual elements are
They're
also
also
matrices.
matrices.
If you really wanted to.
Or you could
It's-
even have it such
It's
that
turtles all the way down.
That's right.
So,
Is
what's,
it possible to have infinite?
Like regression of
I mean,
matrices
yeah.
as the elements of matrices. I bet it is.
what's the characteristic of this ring? This one, right there, not the one with matrices and etc.
Oh, four.
We have a couple claims that it's 4.
4.
I have a third claim. All those in favor?
Say 4.
The motion passes.
Wait, that's not how we do that.
I don't know, in a math search meeting that went just like that yesterday. Why? It's because the one element, in other words, the multiplicative identity, is what? 1 bar, 0 bar, 0 bar, 1 bar.
Sounds like a song.
He does. I kind of make
What's the 0 element? How many times do you have to add, how many copies of this do you need to add to itself to get to this? You need 4 copies. So that, owing to the fact that 1 bar, you have to add 4 copies of 1 bar together in order to get 0 bar in Z mod 4Z. So characteristic ends up being 4. Lincoln.
I appreciate that the characteristic is 4 when it has 4 to the 4th elements.
Oh, I was just about to ask, how many elements does this thing have? Well, we have 4 possibilities for each entry. 4 to the 4 is
256.
216 squared. Yeah, 256. That's not that many elements. This one has infinitely many. Why does that one only have 256?
But it's not 4,
This
so
is-
that's the
This is
interesting thing.
finite.
It's not 256 is the characteristic either.
Right.
Nota bene. So for a finite ring, the characteristic doesn't just have to be the order of the whole ring either. Any questions or comments about any of these? So this kind of gives us a bunch of examples to look off of. Here's a question. One thing I will note is that if we have something like this, 1 plus 1 plus 1, you're adding like n copies of 1 together. That's a bit laborious to write out. So oftentimes you'll just see it written like n times 1. Because if this was in the integers, for instance, that's exactly what this would come out to. Even if n here is necessarily an integer, 1 doesn't have to be. 1 is just the multiplicative identity of whatever your ring is. So here, for instance, we could say n times the matrix 1 bar, or 4 times the matrix 1 bar, 0 bar, 0 bar, 1 bar, and it's just assumed that you're just adding that matrix to itself 4 times. Yes, John?
Does that cause problems if you have different definitions of multiplication?
It sure does. Technically, what we're doing here is treating our ring as a Z module. If that word has no meaning to you, learn some representation theory and come back. Boom! Wicked.
Yeah, there also does seem to be a nice property this goes along with the case where there's characteristic 0,
Mhm.
that if you use the notation that we used for groups at least, which is kind of obsolete when we're talking about rings, but 1 to the n always equals 0 for any ring. If you are using
1 to the n.
if you're using the original group notation where 1 to the n is exactly that.
It is just like adding 1 to itself n times, sure. Yeah, usually when you're talking about rings, having exponents refers to the multiplication operation, and this would refer to the addition operation.
Right. I just didn't know how to express that relationship otherwise.
Sure. You can also do something similar with like any element in the ring, n times r. You could just have like n times r is just r plus adding together n copies of r. Put little dots here to say that we're defining this to mean that. Here's a fun little property that didn't actually make its way into the packet, but it's true nonetheless. Put this as, we can say this as a property, if you want to squeeze this in. If characteristic of your ring is, say, n, meaning you have to add 1 to itself n times in order to get to the identity, for any element r in your ring, what can we say about n times r, do you think?
0.
Would have to be 0. So in other words, we can make the claim that if you add 1 to itself n times and get 0, that should be the same if you added any element in your ring to itself n times. You would expect to get 0. There's a quick little proof. Jonah?
But doesn't that depend on all elements being multiple of 1?
Are all elements a multiple of 1?
Oh, okay.
R equals R times 1. We're assuming here that we have an element 1. That we have an element 1 that we're talking about. And if we do, 1's multiplicative identity, meaning anything times, any R times 1 is just R, which means R is always a multiple of 1, yes. Here's a quick look. Times R, we're going to get R plus itself in copies, which we can use the magic of what property of rings to pull out a factor of R from this. And if we're assuming we have characteristic n, here we have n copies, so this is going to be R times 0, we get 0. So the characteristic of the ring of a ring tells you something about the ring. And yes, and yes, Joda, before you ask, this does work in characteristics. This property does work if characteristic is 0, because then it's just 0 times R is 0. This tells us that if you know how many times you have to add 1 to itself to get to the 0 element, the additive identity, that the same is going to be true for all other elements in your ring as well. That's not to say that n has to be the smallest number of times you add R to itself to get to the identity. Depending on your ring and depending on the individual element, individual elements might not need as much. So like here, for instance, how many times would we need to add this matrix to itself to get to the identity? We just need 2 copies. Well, we need to add it to itself once, meaning we need 2 copies. But what this property is saying is that if you happen to take this, any element in this ring and add it to itself 4 copies of itself together, you'd get the 0 element.
Would that be like moving down a Cayley table to get to the 0 element?
Moving down a Cayley table? Like, in,
Yeah.
what do you mean?
Well, so if you had a Cayley table of,
If you want to have a 256 by 256 Cayley table?
no, because it's just the Z-mod.
Oh, you just want one for the individual entries.
I don't know.
Yeah. Well, it does correspond to the fact that if you added 1 to itself, 1 bar to itself 4 times and you got 0 bar, we had this nice property of, if you think way back to cyclic groups, that the order of a subgroup of a cyclic group has to divide the order of a group. True for any group, by the way, the Rogers theorem. But we first proved that for cyclic groups. Basically, if you were to take 1 bar to any power, which is technically adding one bar to itself n times. The order of that, the number of times you would have to add that to get to 0, would actually be a divisor of how many times you would have to add 1 bar to itself to get 0 bar, which would be 4. Does that make sense?
Yeah.
Yeah.
So is the point of saying that, that's up on the board, that you have to define multiplication that way?
You don't necessarily have to, but when you're talking, but oftentimes that's used as a shorthand notation for,
Okay.
especially when you're thinking about characteristic of a ring specifically. This sort of notation often gets kind of thrown around and used. Does it have to be defined that way? No, but it usually is unless you're working over a weird example. Are we going to see such weird examples? I'm not sure. We'll see. Alrighty, so question. Is there any limits on what the characteristic of a ring can be? Jonah?
Has to be an integer.
Has to be an integer. Can it be any integer?
Has to be positive.
Has to be
Or-
positive.
or, not.
How about let's go with non-negative? Can it be any non-negative n?
Yes.
Yeah, just take z mod nz. Or z in the case of n equals 0. Turns out the same is not the case if you're restricting your rings to talking about fields specifically, or even integral domains. And so our next theorem is going to tell us that if you're working over a field, turns out, or an integral domain, turns out you can only have either characteristic 0 or characteristic prime. So there is no field, for instance, of characteristic 4 or 6 or 9, or pick your favorite non-prime integer. So let's take a look at these. So here's our thing. We're going to let R be an integral domain. Then the characteristic of R is either 0 or prime. I turned around and expected to see Jonah with his hand up, ready to ask about the trivial ring. Doesn't that have characteristic? Didn't we say that as characteristic 1, and isn't that technically an integral domain? Technically. I outplayed myself. I see. Technically that is the case, so fine. Let's go with a non-trivial integral domain.
Or just one prime.
Or treat 1 as prime. Pick your favorite way of getting around that condition. But in a non-trivial ring, that is an integral domain, has to be characteristic 0. Matthew.
What's an integral domain?
Hey, what a coincidence. I was just about to ask you all that. So, you might remind me, what's an integral domain? Like it?
No 0 divisors.
No 0 divisors. Actually means a few things. Here, I'll write it over to the side here. Oh, sorry, Parker. Sorry, Lydia, but you should both know this. Integral domain means 3 things. Means multiplication is commutative. It has a multiplicative identity. You know, kind of nice properties to be able to work with. And the big one, no 0 divisors. Which is equivalent, Matthew, to saying if you have 2 elements in your ring that multiply to give you 0, the only way for that to happen is if at least one of those 2 elements was 0 itself. So the integers, for instance, would be an integral domain. That's where it gets its name. Integral equals integer, because there's no way to multiply 2 non-zero integers and somehow end up with 0. Whereas if we contrast that with something like z mod 4, there is a way to multiply 2 non-zero elements, PCO, together in this ring and get the 0 element
2 bar
times.
2 bars.
Yeah, because you could take 2 bar times 2 bar here and actually get 0 bar, even though neither of these are 0 themselves. So that would tell us this is not an integral domain. Does that make sense? Because like the integers, the reals, z mod pz, where p is prime, would all be examples of integral domains. That's a fun one. It's easy peasy. Beat you to it. One nice property of fields, Matthew, is that all fields are necessarily integral domains. So if every element has a multiplicative inverse, it has to also have that property number 3 there. Not vice versa though. Integers, for instance, form an integral domain that is not a field. So let's prove this. So, excuse me. This is going to be a proof by contradiction, meaning we're going to assume that we have an integral domain whose characteristic is not 0 and is not a prime number, and show that that leads to a contradiction happening somewhere down the line. So let's suppose the characteristic of ring R is equal to n greater than 0 for some non-prime n. And we want to arrive at a contradiction somehow. Well, if n is not prime, what does that tell us about it? If n is not prime, and we're also going to assume n is not 1.
It's composite.
Yeah, it's composite, meaning we can factor it into 2 non-trivial factors, right? So we can say n has to be equal to rs for some 1 less than r and s less than n. So we're assuming we have non-prime characteristic and we're factoring it into two numbers. Well, so what are we going to do? Well, we know by definition, since we have characteristic n, that the 0 element of our ring has to be equal to n times 1, where again, this is just a shorthand for saying 1 added to itself n times. Well, it's just going to be rs times 1. 1 added to itself r times s times, which is the same as taking r times 1, multiplying it by s times 1. And here, this is kind of, Dr. Gerskell, where are you getting this from? This is really from using the distributive property a whole bunch of times. So like for instance, in the case where like r equals 2 and s equals 3, for instance, so rs equals 6. If we were to add 1 to itself 6 times, that is 6. That would be the same as saying, well, we can break this up into 2 copies of 1 plus 1 plus 1. And then say that's just 2 times 1 plus 1 plus 1, or 2 times 1, multiplied by 3 times 1, using this sort of notation.
And the dot on the inside of the parentheses means different things than the dot on the outside of them.
Yes, it does. Multiplication in the ring and multiplication of integers.
Can I just use like a times sign, or would that be going utterly against the normal?
You
So
can do
then I
that
have
if you can do that if you wanted to.
just to keep track.
Yeah, because this is a little bit sneaky. Because here's the problem. We know r times 1, if our ring has characteristic n, meaning n, or r times s, is the smallest number of times you need to add 1 to itself to get to 0, Is R times 1 possibly 0, Isabel?
No.
No, because RS is the smallest number of times, is the smallest thing that if you multiply by 1 you get 0. So R times 1, well that's fewer copies of 1. So that ain't 0. That ain't 0.
We have a 0 divisor.
We have 2 non-zero things multiplying to give us 0, and that can't happen in an integral domain. So that's our contradiction. So this contradicts our claim. R isn't an integral. We have 0 divisors. 0 divisors, Matthew, are when you have things, when you have non-zero elements like 2, well, it's 2, that multiply to give you 0. So, there we have it. That's our proof. If the characteristic is not 0 or prime, then we can't have an integral domain. Therefore, if we do have an integral domain, characteristic can't possibly be both non-zero and non-prime.
And in the proof, we are saying that R is an integral domain at the top.
Yes. Well,
Because it wasn't.
okay. That would. If we want to be crystal clear about it, we should make that part a line in our proof. Now, when I start with suppose it's not n, it's like I'm supposing this condition doesn't hold, but anything I didn't mention we're assuming does still hold. But you're right. If we want to make it like clear what are we actually assuming, we should have a line like let R be an integral domain to start. So all integral domains, and by extension all fields, have to have characteristic 0 or characteristic p or some prime p. I'm actually going to skip the next page and come back to it because you need the page after this for your homework. So here's a fun theorem.
Oh, hello.
What?
You're not a freshman.
There exists a freshman in this class, Eleanor.
Yeah.
I won't point out who in case they want to remain anonymous.
He says, looking directly at you. Whoever you may be.
Surprise, it's Lydia. Why is this called freshman? So this is something that often gets called like freshman exponentiation. A very common mistake that like a high school, this is referring to high school freshmen, by the way, actually do when they're trying to do exponents for the first time. How do I do how do I add two things and take it to the nth power? Why, it's just a to the n plus b to the n, right? No!
Distributed from the
Distributed property.
Yeah, what multiplication are we using?
But it does turn out that if you're working over a field of characteristic p, and if this n happens to be p, then it does actually work out this way.
Well, but doesn't that just mean it's gonna be 0?
What's going to be 0?
The whole thing?
No,
No,
A to the P and B to the P?
no.
no, b
I
equals
thought we
0.
just said that.
No.
Here when we use our exponent, we mean like multiplicatively, not additively.
Okay, just kidding.
He's using.
I know, the notation is just a bear.
That's why I want to use the times symbol instead of the dot.
Go for it.
Well, but the exponents should exist.
So here's
Yeah, but I shouldn't need
Wait,
Anyway.
for which one are you using times symbol?
for the
We're debating.
adding to itself so many times. If I use the times symbol for that, it should be clear. And I will state this in my homework, probably multiple times. But
Hey, that'll help me out. I have no objections.
Then you can simplify.
But I don't think that should particularly come into play in the homework necessarily. So here's the theorem. We're gonna let K be a field. With characteristic p, where for some prime p, I have to ask before Jonah. I have to say before Jonah asks. Then for any A and B coming from the field, A plus B raised to the P power is going to simplify down to A to the P plus B to the P. We can actually say more than this. It's actually the case if you take any power of P, this equation would actually hold. And that's what homework question number 3 is asking you all to prove.
That's chunky and
Oh.
very useful.
In class, we're just going to prove the version where n equals 1.
Mmm.
Ah.
Boy, this is crunchy.
How delectable.
Oh, yeah.
What is scrumptious theorem?
I'm going to make sure we introduce this today so you all have it to work off of. You all have this to work with for the homework over the weekend. And by the way, you don't have to reprove this for the homework. Any result that we've talked about in class, you're welcome to use without proof on the homework. Unless I explicitly say in class, like, how do we know this? It's a homework exercise for you all. Then you need to prove it, but
We kind of explicitly didn't prove it in class when you say that, though.
well, yes. That's why I'm saying that's the exception to that rule.
But you said anything we proved in class. That's something we explicitly did not prove in
Anything
class.
you proved in class, you can use. Anything we didn't prove in class, if you're not, don't assume the result if the problem is to prove the results.
You're breaking your score now.
All right, here's the proof. All right, let's get through this. Why did I say A and B and I used X and Y in my notes? I'm going to go back to X and Y.
I like X and Y better.
So let's say given any X and Y coming from field K. Dr. Gerstle, why are we using K as our arbitrary letter, by the way, to refer to a field?
Because it's okay.
You stole my joke.
Was that?
Yes, I was. Actually, fine, I've got a better one. It's because when you talk about a group ring, where you actually have a ring interacting with a group, use G for group and K oftentimes for field, which is often what you're doing the group ring with. And so you get like KG. And K, where K stands for the field and G stands for the group. Or perhaps K stands for Kevin and G stands for Gerstle. Who knows? But this is actually common use in math and something I found funny when I was learning about this in grad school. All right, let's actually prove this. Given X and Y in our field, we want to take X plus Y and actually raise to the P power. How do we actually have to do this? We can't just take X to the P plus Y to the P. Those
Aren't we proving that we can do that?
Say what?
Aren't you proving that we can do that?
Well, yes, but we can't assume that a priori. We're showing that it simplifies to that. We are going to have an X to the P term, and we are going to have a Y to the P term.
We multiply X plus Y to itself P times.
Oh, that sounds hard,
Yeah.
especially when we don't have a specific value for P.
Yeah.
So
You sound
Andrew?
so sad.
yeah, we're going to have to use the binomial theorem.
The what now?
The binomial theorem.
Here we go. Get ready for some combinatorics. P choose 0, X to the P,
I do love
plus
this
P
theorem.
choose 1, X to the P minus 1, Y. P choose 2, X to the P minus 2, Y squared.
This is the best way to write the general.
P choose, well no, the best way to write in general is like that. Plus P choose P minus 1, X, Y to the P minus 1, plus P choose P, Y to the P. This is from a result called the binomial theorem. No, I'm not going to prove it right now. What does it mean? When we say something like A choose B, what is that actually?
How many ways can you choose B items out of a group of A items when the order doesn't matter?
Yeah, so what number of combinations of B objects you could take from a population of A objects. Take discrete math if you want to learn a lot more about that probability.
Yes,
It
it
does.
does.
Pascal's.
Pascal's triangle.
Pascal's.
That's another way to come up with it. If you have a triangle where you have ones on the outside, and to get each consecutive entry, you add these together.
This is
You go to the,
fun fact.
wait, is it the B8, is it the 8th entry in the Bth row or the Bth entry in the 8th row?
I don't remember.
You pick one
It
row.
works.
You go to that row and then you go to that entry.
You
in
go
the
to
Go
the
1,
eighth
4,
row and
6,
you go to
4,
the
1.
B entry of
Yes,
that row,
that's the one. If you want a nice formula for it, it's a factorial over a minus b factorial times b factorial.
Yeah. It also has lots to do with powers of 11 and powers of 2.
Yes. The powers of 11 work till like the 4th.
Yeah, they
Yes.
always work, you just have to start carrying.
Oh, yeah.
Yeah,
I mean, they're nice
It
patterns
gets
of this thing.
wonky
So.
complicated by
Well,
like
'cause-
row 10,
'cause
but
you
it's still
get-
kinda cool.
So this is kind of a well-known result from like discrete math, combinatorics, number theory. Pick your favorite math class in which these sorts of things start showing up. In Galois theory, I'm gonna call this isn't really a Galois theory. Something Galois theory will use, but okay, fine. So what I want to do is I want to note for any r between 1 and p. We know p choose r, by definition, p factorial over r factorial times p minus r factorial. And here r, by the way, r is referring to an integer, not necessarily an element of whatever ring we're looking at. If we simplify this down, we're going to end up with something like p times p minus 1 times p minus 2 times all the way to p minus r minus 1 over r factorial. And this weird wacky numerator is just what we would get if we simplify that part of the fraction. So like if we were to do, for instance, 5 factorial over 2 factorial, we would get 5 times 4 times 3 times 2 times 1 over the 2 times 1. These would cancel out, and what we have left is you start with 5 and you multiply down to this term plus 1. So what do we know about this? Well, p choose r, we can say a lot of things about it. But since it's the number of ways to take a collection of, to take a combination of r objects from a population of p objects, the number of ways to choose something, that's got to be an integer, right? Otherwise it wouldn't really make sense. Oh, how many ways are there to take a collection of 2 of you from this class? 5.5. Doesn't make sense. So this expression
Just like,
must be an integer. Oh gosh, you're not gonna have enough time for this. All right, let's power through.
no, we're all in Schrodinger's box and then, well.
So what does that mean? Well, it means so r factorial has to divide p times p minus 1 times dot 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 down to p minus r minus 1. So everyone on board so far? So what does that tell us? Well, since p is prime, and r is less than p, that's kind of a starting assumption, r factorial is not going to possibly divide p. Why? Because r factorial is made up of multiplying r by a bunch of factors less than r. None of those factors have a factor of p in it because they're all smaller than r, which are smaller than p. And r factorial, if none of its individual factors divide p, r factorial itself can't divide p, using the fact that p is prime. So if we combine all of that, and I'm not writing this down because I want to finish this right now. No factor of r factorial divides p. So what does that tell us? Well, that means r factorial has to divide the rest of it. The p minus 1 times dot 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 times the p minus r minus 1 part. Well, if r factorial divides all of that, that means p times r factorial is going to divide p times all of this. Just multiplying both sides of that equation by p. And if p times r factorial divides all of that, if we multiply both sides by r, or divide both sides by r factorial, p has to divide p choose r. Because this, all of this divided by r factorial is just what p choose r happens to be. And what does that tell us? That tells us p choose r is a multiple of p. For one less than r, less than p, so that tells us that if we're in a ring of characteristic p, p choose r is going to be congruent to 0 mod p. Hence, this formula down here, so x plus y to the p is going to simplify down to p choose 0, x to the p plus p choose p, y to the p, because all of these other terms are going to go get zeroed out. Because they're all being multiplied by something that's a multiple of p, and p times any element in your field of characteristic p is going to give you 0. And that's just x and p as well. If you simplify those, if you do those factorials. Wabam. Bit of a algebraically a little bit messy of a proof, but kind of comes together to give us this fun result. And this may feel very niche, okay, and tells us something about raising something to the p power in a field of characteristic p. How is that going to be useful for us? The answer is very, which we will see in due time. Have a good weekend, everybody. See you all next Tuesday.
Wait, don't we have-
Yeah, class ends at
15.
It's 12:15. That's dang it. I am not used to this Tuesday Thursday schedule business. Why did I think it was noon? Yes. No.
I was just wondering why it only works when p is a prime. Are there others that pop up? I mean,
So p prime kind of is required for this part.
yeah, we used it there, but I was what? Are there?
4 doesn't divide 4, choose 2.
Right. Okay.
That. Yes, that. Thank you for giving me, helping me come. Thank you for giving me a good example to work with. Yeah. The fact that p is prime is necessary to say that all of these are multiples of p. And yes, it thus are congruent to 0 mod p. If p was not prime, these would not all have to be multiples of p, and thus you get more complicated expressions that show up.
So you might end up with like a bunch of them would go away, but not all.
Correct.
So does this work with infinite rings?
We didn't rely on the fact that the ring was finite anywhere, did we?
Or no, that, like what if they have a characteristic of 0?
Huh. Well,
It's just gonna be 0.
well, that's technically 1, and x to the 0 plus y to the 0 would be 2, at least over the integers.
Yeah.
So no, it wouldn't actually work. Gotta be characteristic p.
Interesting.
Any other questions or comments?
So what about negatives though?
Don't go there. Yes, I'm asking you to prove this for p to the n. No, you don't necessarily have to do a super combinatorially messy proof like this for number 3 on the homework. Let's see, if I would recommend trying some mathematical induction, the homework version, because we just proved the base case, n equals 1. The zombies in the corner are pleased.
Induction means more brains.
Yep. So let's go back. Let's talk briefly about the theorem that we skipped, because this one I'm not really going to prove much and leave most of the details up to you. Turns out, if you know what the characteristic of your field is, you could say something about the subfields of your field. In particular, in any field, and yes, Eleanor, this works whether or not k is finite or infinite. We can say that for a k field, turns out we can say if the characteristic of k is 0, then k has a subfield isomorphic to the rationals. The rationals, which are themselves, can be written as quotients. And you have characteristic P. What's your favorite field of characteristic P? Zima peasy. So it's not the only one, as we've seen. K has a subfield. It is isomorphic. Zima peasy. So let's take a look at how we would construct each of those. It's actually not hard. You basically just use one. Here's a big hint. Use 1. So here's my proof for part A. We're going to define a set P of k to be equal to the set of all elements of the form n times 1 divided by n times 1. Where m and n are integers, n not equal to 0. Since we're working over a field, we know we can do this. We know n times 1 is going to be non-zero because n is non-zero, and because we're working over a field of characteristic 0. So adding 1 to itself a bunch of times will never give us 0. So we're working over a field, we can divide by any non-zero element we want. So like this. I claim that P of k is isomorphic to Q. How do you think you would find such an isomorphism? Lincoln, you look like you have a thought.
I don't actually know where to start, just because that's basically how I would define the rationals in the first place.
Oh, hey, so maybe move map m times 1 over n times 1 to
M times 1.
m over n,
Yeah.
where the time, I'm just going to say m over n, the rational number, whereas this, 1 is likely not an integer, depending on what your ring is. So this is very much not a rational number, probably. Unless your ring happens to be like the integers, in which case that's not a field. So checkmate, you can't do that. Part B, do something pretty similar. We're going to let P of k. Here we're assuming we have characteristic P. So what we're just going to do is I'm going to take 1, 2 times 1, 3 times 1, up through P minus 1 times 1. I claim this is going to be isomorphic to Z mod PC as a field. we end at p minus 1 times 1 because if we were to do p times 1, that would get us to 0.
Wait, don't you want it?
Do we want to?
Because you're starting with 1.
You didn't start with 0.
We want to have p elements. Oh yeah.
We have P minus 1 elements right now, I think.
Yeah. You don't have, yeah.
Let's throw that in there. Yeah, because if we want a field, we definitely need a 0 element.
There we go.
And then it starts looping.
Yeah.
Oh no, then it stops actually because then it loops around. Yeah. In each case, we call this the prime subfield of K.
So those are the P of Ks?
Which is defined, as you can see, is defined a little bit differently based on whether you have a field of characteristic 0 or a characteristic that's prime. And we don't have much. We can't do too much with prime subfields right now, but but it's important that they exist because that's going to be important later for when I actually introduce the word Galois into Galois theory, and we start doing something called Galois extensions of our fields.
What does this subfield mean?
It's a subfield. It's a smaller field. But it's like subring, but it's a field.
It's a field inside a field.
That forms a field under the same operations as the larger field. Just take your definition of subring and replace ring with field. It's a specific type of subring, I guess.
Why prime?
Why what?
The y prime?
Because it has to be a field.
Well, because it has p elements in it, complicated reasons that we'll get into much later in the semester. I mean, for this one, it's easy to just say, oh, because it has p elements, and every field with exactly p elements has to be isomorphic to Z mod p. Actually, we actually proved this in 410. Well, actually just proved it for subgroups, but for subfields or for groups, but for fields it's pretty much the same.
Well, we actually need prime for the characteristic to be prime, because then it's a field.
Well, yeah, but well, yeah. I mean, yeah, we're basically saying if you have a field, then it has to be in one of these two categories from the theorem we proved earlier.
Is every subring of a field a subfield? No, right?
Nope. Here's my counterexample. That's a field. That's a subring. That is certainly not a field.
No.
So true.
So
All right. I think we'll call it that for today. That finishes off the packet. There is. Oh, yeah, but I answered that in class. Do all infinite fields have characteristic 0 and finite fields have characteristic p? No, we've already. A finite field has to have characteristic p, but an infinite field could have characteristic 0 or p. That's what I was going to say about that. Maybe I'll write that down in the Lorestar class next time. Yeah, next time we're going to be talking about a special type of integral domain called a Euclidean domain. Y'all remember the Euclidean? I'll give you a hint. You might want to brush up on the Euclidean algorithm over the weekend,
Oh boy.
because it's going to be coming back on Tuesday, but over an arbitrary ring instead of just the integers.
Gave me a website with like a bunch of cats.
Oh,
that's
and
on
the-
it.
By the way,